Hello, everyone. So today I'm going to share with you some tips and tricks for basically launch your next large-scale batch ETL job. So first, let me tell you a little bit about Newstar. At Newstar, we provide a range of cutting-edge marketing solutions. You can actually find out more information on that link right there. On our team specifically, we focus on helping the world's most valuable brands basically understand and target their consumers both online and offline. So we help them maximize their ROI on ad spend. And in terms of data size, we deal with billions of user events per day, and that's petabytes of data. So word here on our stack, all of our Spark jobs are on AWS EMR. We read from S3, and we output to S3. So we built a lot of infrastructure around our data pipeline to ensure things are fast and fault-tolerant. So if you look at the middle section here in the blue box, all of our Spark jobs are actually batch ETL jobs, which is our focus today. So what makes batch jobs different? Well, with batch jobs, as opposed to like ad hoc data science uses or streaming, we really care about robustness and reliability because it usually runs on a schedule where it's programmatically triggered. So there's no manual intervention if things go wrong. There's no manual person like monitoring the job. Another focus of ours is we really want the complete utilization of cluster resources, especially memory and CPU. So depending on your workload, if you have a streaming application, you might not care that your cluster is being used 100% second to second, right? But this is actually our focus for batch jobs. So why do we use batch so much? Well, for us, we care a lot about historical state. In fact, most of our jobs, most of the data we load is historical. The other thing is we don't really have an SLA other than 1 to 3 times daily delivery. And for us, we really care about the efficient and tuned optimal use of resources, so really about cost efficiency. So let's talk about the things we're going to talk about today. So first, we're going to delve into some specific issues that only happens at scale. Then we're going to talk a little bit about data skew, or when outliers really affect your performance. Then we're going to talk a little bit about optimization strategies, and then finally, Ganglia. So to get started, let's talk about a very specific problem. So this is a problem that's really relevant to our business. We process large quantities of ad events, so some familiar events include impressions or clicks or conversions, and the problem we're going to focus on today is called the attribution problem. It's basically when we want to find out which impression or click contributed to the conversion. So let's make this a little bit more concrete. So Alice goes to her favorite news site and sees 3 ads. So these views of ads are called impression events. She then clicks on one of them, and it leads her to Macy's, and that's called a click event. Then she proceeds to buy something on Macy's, and that is called a conversion event. So the problem here, the core of the problem here is basically how can we attribute her purchase? Like what impression or click caused her to want to purchase? So how do we solve this in code? So basically, we want to join the conversion events with impressions and clicks on the user ID. Then we basically construct a collection of events per user. We iterate over the events, and we basically find out for the conversion events which impressions or click that happened before it likely caused it. So later, so the target event timestamp really matters because we assume that target events that are closer to the conversion are more likely to have caused the conversion. So in terms of the scale of the data, we're loading 90 days of data. For us, that means around 250 billion of impression events, 20 billion clicks, and 50 billion conversions. So in terms of the larger part of the join, we're joining conversions on impressions, so 50 billion joining on 250 billion. So that Venn diagram there is actually to scale in 2D. OK, so let's delve right into the topics. So once you're working with this kind of data, where you're having like hundreds of terabytes of data being loaded, you're going to run into very weird and specific problems that nobody else has ever seen. So for example, you might see this stack trace right here on your driver. So you're like, oh, wow, I'm out of memory. Let's go check our metrics and look at what our heap is up to. And you realize that you actually have a lot of heap left. So you can increase your cluster size by a lot, like your node size on the driver by a lot, but it's not going to do anything because you have lots of heap left. And so you're like, what's actually going on? Well, if you look down a little bit, you see that the byte array output stream is actually trying to grow, but it can't because it's hit max in. And you're like, So it's Java's inability to allocate an array that's happening here. And you're like wondering, so what's actually in this byte array output stream? And if you look down a little bit, you'll see that there's a hint right there. So what's actually in there is an array of map statuses of size m, where m is the number of mappers. And each of these map statuses contains information about how the block is used by each reducer n. So already you can tell this is an m times n problem. So in Spark, there are two types of map statuses, the compressed and the highly compressed. And if you have more than 2,000 partitions, Spark is going to use the highly compressed one, which includes some optimizations to reduce your memory usage. So it's going to track a reduced partition average size and a bitmap that tracks which blocks are empty for each reducer, instead of a map that tracks exactly what the size is for each reducer. So even with the highly compressed map status, you can see it's still an m times n problem. If your map output goes to a random set of reducers, so the bitmap is not going to be highly compressible, you can still run into this driver ON issue. So luckily, the solution is very straightforward. You need to reduce the number of partitions on either side. So for us, when we went from 300,000 mapper partitions to 100,000, this error went away. So another really important thing to take note of when you're dealing with large data is this periodic GC interval setting. So as we know, major GC cycles stop the world, right? Your CPU is going to be idle in the time when it's going to GC. When we're dealing with a large amount of data, we're using usually really, really large clusters. And you have large heaps, which means GC cycles are going to be longer. So in order to overcome this, we actually set this property to something really, really long that we know for sure is going to exceed the amount of time the job actually takes to run. So a little bit more detail here. Spark has this thing called context cleaner that uses weak references to basically register the things that could go out of scope. For example, RDs, shuffle dependencies, broadcast variables, et cetera, et cetera. And then this periodic GC service will come in periodically as specified by the property from the last slide. And it's going to come in and garbage collect these things. So this, you can see, is probably really useful if your application is really long running, like a streaming application, where it needs to be on for like days or even months, so you don't want to run out of disk space. But for us, because we're batch and because we don't want to waste our CPU and resources, this is never useful for us. Another thing is we really need to be patient with our machines, basically. They need a little bit more time to communicate with each other. So these are the two settings that are relevant. As I mentioned before, because our heap is so large, our GC takes a long time. So if you go into GC, you're probably going to exceed the default timeouts already. And an example of a stack trace that basically tells you need to up this number is shown here. Another thing is, when you're reading millions of files from S3, it's going to be flaky. You're going to have misconnections. So you got to set this max failures to something higher than the default of 3. For us, we found that a number between 5 and 10 works the best. And the reason we don't want to go over a reasonably large number like 10 is because if something really bad does happen, and it's a real error, you want to catch it as soon as you can and deal with it as soon as you can, and you don't want it to go into this retry cycle forever. OK, cool. So now we're going to move on to data skew. So when you have large data, you're probably going to have some kind of skew. For us, we had extreme skew. We had a few users for this 90-day period. They had like more than 100,000 events on them, whereas the average user has fewer than 50. So our executors were dying because there were a handful of really, really large partitions. So graphically, this is what it looks like. As you can see, most of the users have fewer than 1,000 events on them. And in fact, most of the users have fewer than 50 events on them, but the tail is very long. So if we zoom in a little bit to the very far end of the tail, you can see even though the tail is long, the number of users affected basically have this pathological behavior is very few and far in between. So the number one thing that should come to your mind is increase the partition number so your data is more spread out. The other thing that should come to your mind is you want to nest your data. So you don't join the events, the conversion events, by impression events. You nest it by user ID first, and you join the list. So this avoids the Cartesian join, where perhaps one row becomes 10 rows after a join. So after implementing these two strategies, the job is running. So yay, great. But you can see on the Ganglia graph, there's this huge period where the CPU is not doing anything. And in fact, it's actually stuck on like a handful of tasks, the tasks that have a lot of events on them. So here's another view on this in the Spark UI. You can see the median duration of a task was 24 seconds, but the max was 50 minutes. So what else can we do? Well, if you have domain-specific knowledge, in our example, it would be like, I know ahead of time which users are going to be bad. I can filter them out ahead of time. Or another oft-told strategy is to salt your data with a random salt, and then shuffle it twice, and then ultimately arrive at the key that you want to arrive at. But remember, in Spark, shuffling is super expensive. So in practice, this was never worth it for us. Another strategy is to use something called a Bloom filter if one side of your join is much larger than the other. And I'm going to go into detail in this for a little bit. So what are Bloom filters? Bloom filters are probabilistic sets. So basically, it can answer the question of whether an item belongs to a set probabilistically. So the size of a Bloom filter is mainly determined by the number of items in the filter and the probability of false positives. And in this context, false positives mean that the filter tells me something is in the set where it's actually not. The very, very important property of Bloom filters is that there are no false negatives. That means it will never say something is not in the set where it actually is. So that's very important because to use this as a filter, we need this to have no false negatives. So how do we use this in practice? So in practice, basically, you can have your executors load the data, and then you can do a tree reduce on the data, and then collect that on the driver, and then broadcast the Bloom filter out to the executors again. So a thing to note here is, please don't feel like you need to use a really low false positive rate. A really high false positive rate is still really good for filtering purposes. At 5%, we'll get 80% filter out, and the subsequent join is going to be much faster. So the thing to note here is the trade-off is really between accuracy and size. And if you have Bloom filters that end up smaller than 5 gigs, it's probably going to work out for you. Please experiment with Bloom filters. There are a lot of really great papers online about this. OK, so let's go back to our problem. For 50 billion conversions, which is the small side of our join, a false positive rate of 0.1%. Our filter was 80 gigs. 5% false positive rate. Our filter size was 35 gigs, so it was still too big to be feasible. What are we going to do? So we tried all 3 things, none of them directly applied. And we still have this ugly, ugly Ganglia graph. So at this point, it's really important to know what your threads are actually doing when it's in this long tail process. And on our 16 core executors, we noticed that all of the threads are basically stuck doing this, and it's writing to shuffle space. So for the pathological partitions, there's so many events, and it's taking so long to write to shuffle space, which essentially means in order to make this long tail go away, we need to reduce the data size before going into the shuffle. So let's go back to the data. So we looked at just the pathological cases, and we noticed that the ones that were pathological, most of the events had similar information. They were for the same campaign, for the same sites, but they were spread over time. Which gave us the insight that if we just retain 1 event per hour at 90 days, it's around 2,000 events, which is definitely dealable. But if you think about this, if we retain 1 event per hour per user, that means we need to group by the users first to get the collection, right? And we know group by key invokes a shuffle, right? So that means we can't do this, because we need to reduce the data size before going to the shuffle. This is where map-side combine comes in, and it's a really, really important feature. And we can use this combine by key method to basically maximize the map side combine and basically reduce the data there so less is written to shuffle space. So here's a code example. And I know it's hard to read, but this will be online later. And if you notice the second lambda there, that's actually on the map side combine side. So this is still on the map side. And if my collection exceeds a certain size, I'm going to basically thin it out. And you don't have to implement it this way. The reason we do it this way is because, as you saw in the previous graph, we have very few users that have this bad behavior, so we don't want to apply this method to every single collection. But for your use case, you might not care, so you might want to just thin out every single collection. So you implemented these 2 methods, and you got rid of the long tail. Hooray! But perhaps you want to squeeze even more performance out of your cluster. So what are you going to do? This is where we're going to talk about optimization strategies. So I'm going to repeat this a lot during the presentation, but you want to avoid shuffles. And the easiest way to do this is to reuse the same partitioner instance. So this is an example DAG, and don't try to read what's going on. It's impossible. Just notice that in the red box here, there's actually 3 combined by key operations and 2 left outer joins. And they're in the same narrow transformation. So if I use different partitioners for each of these steps, then each one would have resulted in a shuffle. So can we even go further? And the answer is yes. We're willing to go further to avoid shuffles, and we're willing to pay for it in memory. The way to do that is you want to denormalize your data or union your data to create like a master set. And then we're going to rely on the fact that we're going to reduce into a highly compressed key space, and we shuffle only once. So let's use a specific example here. OK, so assume you have this data coming in, and you basically have user events. And it has user ID, campaign, and site. For example, Amy, she saw a campaign about shampoos, and she saw it on Google. And then Bob, he saw a campaign about conditioners, and he saw it on Yahoo. And the end result we want to get from this RDD is we want a count by campaign and a count by site. So for example, for the shampoo campaign, there were 2 events on them. And then for the Google site, there were 2 events that happened. So if you just think about this in a very straightforward way, you probably want to cache the initial RDD, and then you do a reduce by key on campaign, get the count by campaign, and then you do a reduce by key on site, and then you get the count by site, right? But this is 2 shuffles. So instead, what you could do is you take each row, and you duplicate it. You duplicate it once for the type of summary that you want to get. So in this case, there's the site, which is what I call an output enum that I mark it there, and then I extract the site key out. And then I do the same for campaign. So basically, we're doubling the size of this RDD. So once we get this pair RDD, we can reduce just once and then filter the end result by either site or campaign to get the 2 summaries that I want. And you can see this only results in 1 shuffle. And this, for us, has always been worth it. So another strategy that really, really helps with your performance is coalescing your partitions when you're loading. So if you're loading a lot of small files, for us, we do, you want to make your partitions contain more tasks, basically. Make your partitions contain more files. And you know that coalesce does not invoke a shuffle, so it's cheap. And you're going to reduce your task overhead because each task has a bunch of overhead stuff. So now your CPU is probably going to spend more time doing actual computation instead of dealing with overhead. So for us, when we went from 300,000 loading partitions to 60,000, we actually cut the loading time by half. So this is a code example of what's going on. So you can see it's loading from S3. And then you can get the native partitions right there. And then depending on how dense your data is, you can apply some algorithm to find out what your coalesce partition is, and then apply that. The coalesce actually affects all the narrow transformations above it, not just one. So that's pretty cool. And then subsequent operations will be more efficient. OK. Another counterintuitive strategy here is actually to materialize your data, perhaps ahead of time. So this really works when you have a large chunk of data persisted in memory, and then you are going to calculate some smaller RDDs off of this large one. So you may want to actually materialize the smaller RDDs with an action first, so then you can mark the larger RDD as unpersisted, and then use that as execution memory instead. So here's another example, pseudocode here. And then, so if the parent RDD is super large here, and then you're calculating a bunch of child RDDs off of it, you may want to do an action like a count or a reduce on the child RDD, and then mark it as unpersisted. And it's important that you perform a random action first. You might not even care about the result of the action. You might just throw it away. But it's important here because Spark is lazy. And if you don't do this and mark it as unpersisted before, it might go back to the source and try loading it again. OK, so now we're going to talk a little bit about Ganglia graphs. So Ganglia is super useful for understanding your performance bottlenecks. You saw a couple of examples earlier in the slides already. And we really use it for tuning our clusters. It's available on AWS EMR, so it's very simple to use. So here's a use case right here. You notice that within the same stage, there's a lot of fluctuation here. There's like this wave pattern. And sometimes it's tighter like this, or sometimes it's looser where like crest to trough, you have like 10 minutes or so. But really what's happening here is you're going into GC multiple times within the same stage. You don't have enough execution memory. So for us, the easiest solution is to persist to disk only. But this really depends on your machine class. For us, we use R3s, which has onboard SSD, so it's really, really fast, so it's always great. But if you are using R4s and you have like EBS volumes attached to this, you gotta really tune and test and figure out if this works for you. In our tests, it has been, but again, tune and test. Another example here. So this happens a lot, where your earlier stages are running really well, you're using like 90% of your CPU, everything's great, but then there's one stage that suddenly drops and it uses only like 70% through the whole time. So you're wasting like money and resources, right? Because you're still paying for the full cluster. What does that mean? This usually means you need to decrease the number of partitions for the RDDs used in this stage. So for example, if in this lower stage you're using like 2 different RDDs, then you want to repartition the RDDs that feed into it into smaller number of partitions. And this is important because the more tasks you have, the more total task overhead you have, which means you're going to spend more CPU just dealing with the overhead. And the other thing is, when you have fewer tasks, each task actually computes a little bit more of your total computation, so you're actually dealing with more computation per task. So after we decrease the number of partitions, this is our Ganglia graph, which is very, very pretty. OK, here's a final word on our configuration. You can see here that for this data set, we're using R34XLs for both the master and executor. So over here, we have around 1,800 cores. And then the configurations here, most of this we actually talked about during this session right now. There are a few that I didn't talk about, but Spark is usually pretty good about telling you explicitly when to set these. For example, like overhead, I'll tell you perhaps set memory overhead. But if you have any questions about this, feel free to ping me after the presentation. So in summary, large jobs are really special. You want to use special settings. You can outsmart the skew with the strategies I outlined earlier. And finally, use Ganglia. So that is my presentation. Thank you.
Thank you, Emma.
Yeah.
If you have any questions, we got 2 mics right by the camera. Please keep them short, keep them succinct. Anybody? Well, give a big hand to Emma then.
Thank you.
You can actually go ahead if you want. Yeah, please. We have time.
Sorry, I'm going to take a really quick photo. I did this whole presentation for this photo, so. All right, cool. Please go ahead.
Yeah, on your last slide there, I noticed you had dynamic executors turned off. I'm just kind of curious why you did that.
Sorry, can you?
On your last slide, you had dynamic executors turned off?
Oh, yeah, dynamic allocation?
Yeah,
so,
yeah. Why did you do that?
That's useful if you have multi-tenancy. Like you have multiple things running on your cluster. We never do that because we're batch jobs. We want to use 100% of our resources doing just this one job. We never want it to be like, oh, release these executors because we're not using them right now. That also takes time. Even if you have it on, this job will probably run perfectly fine. It takes a while to release the executors and recall them back, so it's just a waste of time.
OK.
Yeah.
Anybody else? Going once? Twice? All right. Emmy.
Oh, there was a hand there. Was there a hand? Yeah.
Yeah, do you mind walking up to the mic, please, because it's hard to hear you.
There was a suggestion to duplicate an RDD to avoid shuffling, but isn't that against the memory constraint?
Yeah, so I mentioned really quickly that to avoid shuffles, I was willing to basically pay for it in memory, which means that I'm going to use more memory in order to avoid the shuffle. And if you have enough memories like we do, it really depends on your stage. If you know that if you duplicate your data and your RD is super large, you're going to exceed the memory that you have, don't do it, right? You just can't. But if you can do it, it's always worth it to do this instead of doing multiple shuffles.
Okay, thank you.
All right,
Okay,
thank you
thank you.
guys.
We'll see you back here at 2. We have 2 birds of feather session going on by the lunch. One is called Apache Spark Meetup Organizers, BOF, and then Apache Spark on Kubernetes. So bring your lunch, ruffle some feathers, and